our next speaker, Diana Chang, and Diana is a senior solution architect at Amazon Web Services, where she works with enterprise customers to help them achieve their business goals through the adopt of cloud technology. She has 10 plus years of experience in software development and consulting. During that time, Diana joined sorry. Before AWS, Diana worked as a team leader, architect, and consultant at number of enterprise companies in different sectors. Diana will talk today about integration patterns for microservices. Really interesting topic, and please don't forget and send your questions to Diana, and the best question will get AWS credits and special prize from NX.
Thank you very much for having me. My name is Diana Chen, and I'm a Senior Solutions Architect at AWS. And I've brought to you today a talk which is based on the content originally developed by a colleague of mine, Dirk Fruner. And in this talk, I will explore some patterns to help you architect for independent systems that can evolve, scale, and operate individually, and where you have resilience in the communication amongst those systems. So when we talk about system designs, we come across two very important principles, divide and conquer and loose coupling. And microservices is already a very good way to apply divide and conquer. And in order to reach loose coupling, asynchronous messaging is a pretty good mechanism. But we don't, when I talk with my customers, I don't often see that or hear that they have this in mind. So I hear REST APIs, but they often forget about the possibility of asynchronous messaging for loose coupled integration. So that's why I want to present this today to you. The patterns that I've brought today can be applied not just for microservices, but are of general use in system integration. But let's take a look at the agenda. So I will discuss a little bit more the motivation for this talk and why we have to discuss this in the first place. And then I'm going to introduce the fundamental integration patterns, all of them based on asynchronous messaging. And to make it more tangible, I also brought some use cases so that we can see how the patterns are applied. So to motivate the topic a little bit, I would like to start with a quote from a former colleague of ours, Tim Bray. And he says that if our application is cloud native, large scale or distributed, and it does not include a messaging component, then there's probably a bug in there. And I think that's absolutely right. And the reason for that is because if we think about a landscape of microservices in our backends, and we think about those requests that's coming from the outside, those requests probably need to wander through a number of services before they get fully processed. And if we have synchronous communication in each step of the path that our requests need to follow, then we are probably blocking some resources because every path is waiting for the subsequent one to get done. As you might imagine, if we encounter a problem in some of the downstream systems, then this can easily accumulate upstream, and we can put our entire end-to-end system at risk, especially if the upstream components start retrying the request. And that's the reason why we have mitigation patterns like circuit breaker, for example. But other than that, there are simply certain things that will just take too much time, and we shouldn't be waiting synchronously for them to happen. And other things are just typically asynchronous in nature. And with that in mind, I'll start introducing now the patterns that I brought today. And I mean, if you're an architect or a software developer, you're probably already used to talking about patterns because patterns are really a very generic way to talk about things that we have in common. It's kind of like a lingua franca or common language. So when we talk, we understand what the other means because it's something well established. And if we look at software development, for example, then we have the gang of four patterns, that catalog of software patterns. You might already know it. And when it comes to integration patterns, there is also a catalog that I would consider a standard catalog for integration, which is the book Enterprise Integration Patterns, authored by our AWS colleague Gregor Hoppe and Bobby Wolf. And you can read and find out more about those patterns also online on Gregor's website. So here you can take a photo of this QR code and then go to the website and visit and read more about the patterns that I will be discussing, some of which I will be discussing today as well. So let's start from the beginning. We are going to discuss integration and asynchronous messaging. So first, let's define how a message exchange works. So how do we send messages from one end to the other, and what is the reaction or response that we expect? And the first mechanism of message exchange is a one-way communication, and it's really quite simple. We have a sender on the one hand and a receiving on the other, and the sender sends a message into a message channel, and the receiver receives it. And that immediately shows you that this messaging channel in the middle is decoupling the sender and the receiving from each other, because due to this component, podents don't need to know about each other. The expectation here is, I mean, in this case, that there is no response because it's a one-way communication. So we simply need to send the message by putting the message in the channel, and that will eventually reach the receiver. The message that we send across to the message channel can have multiple intents. One purpose could be, for example, a command type of message. So when the sender wants to instruct whatever is on the other end to do something, or a document message. So if we just want to transfer some data to the receiver. And there are also event type of messages. So when we just want to notify a receiver about something, and it's up to the receiver to know what to do with that message information and how to act accordingly. In contrast to this one-way communication, we also have the request-response pattern. And here we not only have one message channel, but we have two, because one of them is for the request and the other one for the response. So the requester sends a request message, message A, for example, into the request channel, and the responser receives it and it works on it, and then sends back a response via a different messaging channel. In this case, it's message B. And this immediately raises two questions. So if the sender and the receiver are decoupled, how can the responder know where to send that response? And how can the requester also know to which previous request this response is for? So these questions are addressed by two mechanisms, and one is called the return address, and the other one is the correlation ID. The return address is a small pattern that means that we put a small piece of meta information in the request message, maybe in the header, so the requester injects that, and the responder can extract that information from there and use it to identify the message channel for the response. So it will typically contain the response channel address. The correlation ID pattern means that the requester inserts some meta information into the request that identifies that unique request. And the responder is asked to forward this back when he creates the response and puts it in the response channel. So the receiver can know, oh, okay, I need to correlate that to that request that I previously sent because I have that request ID. And we can further distinguish between the patterns that we have here. What we see on the left-hand side is an integration pattern. We simply integrate the left and the right-hand side of the picture by using the messaging channel in the middle. And on the right-hand side, in contrast, we have an actual conversation between the requester and the responder. So this is a composite pattern. We call it a conversational pattern. So we've been talking about messaging channels, but it's been rather abstract. So what kind of messaging channels do we have? The first one are point-to-point channels, and they're implemented by queues. What we see in the diagram here is that we have a sender, and the sender sends messages into a queue. And one or more receivers that we have on the right-hand side, I mean, we can also have multiple receivers, multiple senders, but for the sake of simplicity, I've only included one here. And what happens here is that the messages get delivered into the queue, and each message is delivered to only one receiver. So message A goes only to receiver 1, message B only to receiver 2, message C only to receiver 3. And if we look at the potential situation in which the queue starts receiving a lot of messages, which might overwhelm the receivers or consumers on the right-hand side, what we can do is simply add more consumers so that we can deal with more messages, because the messages will distribute across the receivers. So each additional consumer is adding some capacity to consume those messages. And like this is very easy to scale on the consumer or receiver side. And this is because the message queue is also acting as a little bit of a load balancer. And it's also queuing or buffering the messages for us. So this can help us flatten peaks of load that come into our system. The queue can retain those messages for a while, for as long as it's necessary. So we don't need to necessarily scale on the receiver side. So if we say, hey, I don't want to add more receiver components on the right-hand side, I want to take my time to process the request, that's totally fine. The messages can stay in the queue and the receivers can work at their own pace. And you, for example, if you want to save cost and not scale more, then that's also possible. You can do this because you have a queue there coping with that load for you. Another fundamental type of message channel is the publish subscribe type of channels, and these are also known as topics. And their behavior is different. It's actually a fan out behavior. What this means is that we have a publish subscriber scenario. And here we have the publisher. So we previously called it sender, but because this is a publish subscriber scenario, we call it the publisher now. And our receivers are now called subscribers. What happens is that the publisher sends a message into the topic and each subscriber receives the message. Each subscriber will actually receive every message. So instead of receiving one per or a different one per subscriber, we're actually pushing all messages to all subscribers. And we can compare this mechanism to switching on the radio. When we switch on the radio, we start listening to it and we start getting all the information that gets sent. But if we switch off the radio and stop listening and come back 1 hour later, we would have missed what happened during that period of time that we weren't there. And this is also what happens when we have topics. Topics try to reach their subscribers and send the information that they receive, all the information that they receive to their subscribers. And if our subscribers are offline or they're down because they run into a runtime failure, they will miss those messages. And the different products that are available in the market will, of course, behave differently and will implement different retrying mechanisms to deliver those messages to the subscribers. But conceptually, there is no buffering mechanism for message topics. But another question that probably comes already to you is, if every subscriber receives every message, what if the pure amount of messages that the topic gets is actually just too much and it starts to overwhelm all the subscriber processes that we have? If we add one subscriber, another one subscriber, or even more, it doesn't really make a difference because they will also get all the messages delivered. So we can't scale on the subscriber side just by adding more subscribers. It's not the way it works. And so we need to think here of something else. And I'd like to park that question for a minute, and we'll come back to this with a solution in a few minutes. But first, I would like to mention what concrete AWS services we have that helps us implement those messaging channels that I've just mentioned. So I will start by mentioning our serverless services, because these are the ones that I showcase later in the use cases that I discuss at the end of my talk. And for queues, we have Amazon Simple Queue service, so that's Amazon SQS. And for topics, we have Amazon Simple Notification service. And just for the sake of completeness, I will also mention that if you are, for example, constrained to using other protocols for messaging like JMS or AMQP, in that case, we have Amazon MQ, which manages a RabbitMQ or Apache ActiveMQ broker on your behalf. And these are typically used for workloads that currently reside on premise and that we are thinking or planning to lift and shift into the cloud. And you might also ask yourself, but what about streams, right? You might be familiar with streams already. And streams sound or appear quite similar to topics, and in fact, they are because they both implement a fan-out pattern. But there is a slight difference. So with message processing, what we actually mean is that we work on each individual message as a unit of work. And so every message that comes in, that message has a value in itself and it gets processed individually. And once we have consumed it, it disappears from consumption from the message for consumption from the messaging channel. And to visualize here a little bit, I have this picture on the left-hand side, and it represents a message that is worked on as a unit and gets processed as a unit. If we look at stream processing, we have the same picture again, but now we have divided it into numerous tiles. And as you might imagine, in this case, every tile in the picture, every little piece is a message in the stream. And with streams, we're usually not interested in individual messages, but we're interested in batches of messages. The batch of messages becomes the unit of work when we talk or discuss or work with stream processing. So we won't look at one message in isolation. We will look at batches of messages in order to identify things like trends or calculate aggregates and so on. And another difference when we talk about the streams is that once we consume messages from a stream, they will remain in the stream and we can consume them later too if we want to. We typically say that the stream can be replayed at a later time until the expiration time has fired and some of the messages have disappeared or moved out of the stream. So we have this retention period, this rolling retention period within streams, and the duration of that rolling window is dependent on the concrete product that you use, but it's typically configurable. And you might also be wondering about buses and more precisely about event buses. So event buses also implement the fan-out pattern, and they're similar to message topics, but these are more purpose-built type of services. So they usually come with integrations for commercial software. They come with advanced message routing options, and they're a little bit more opinionated on how the payload should look like. So they come with a lot more functionality than pure messages topics, the topic messaging. But for all intents and purposes, there's really no conceptual difference between the both. And we're going to treat event buses and topics for the remainder of this talk equally. And also to summarize the AWS services that we have available for streaming, so for implementing the fan-out pattern also with streaming, we have our cloud-native and serverless Amazon Kinesis family with Kinesis Data Stream, which is the service that actually implements the stream. We have also Kinesis Data Firehose. For example, when we want to offload batches of events, we discussed the batch of events, into a sink, into an object store such as Amazon S3. And we also have Kineta Data Analytics to run analytics on sliding windows or on batches of streams, for example. If you are, again, constrained to working with open source software, for example, Apache Kafka, there is also Amazon Managed Streaming for Apache Kafka that will manage a Kafka cluster on your behalf. And since we have also mentioned buses, there is Amazon Event Bridge as a cloud native and serverless event bus on AWS. And yeah, with that, I would like to move on to talking about other patterns. And this pattern is the topic queue chaining. And with this, we can address the question that we raised before of how to scale consumers on the right-hand side of the publish-subscribe channel. And actually, this is the solution for it. So let's take a look. We again have a producer, and this producer sends messages into a topic. And the topic will fan out those messages. And now what we can do is apply a composite pattern. So that this is what we call the topic keychain pattern. So what we do here is that we won't directly attach our subscribers to the topic. So we won't attach our subscribers directly here, but we will put a queue in between. The topic will simply fan out the messages will go into a queue, and we will have our consuming the messages from that queue that will now sit in between. And this really brings us the best of both worlds, because on the left-hand side, we have the fan-out functionality with the topic, but we can also now scale on the consumer side because we have put a queue in between. The queue will provide us with a load buffering functionality. It will retain the messages until we can process them at our own pace. And yeah, and if we add more consumers on the right-hand side, we can do more things if we, for example, wanted to do some parallel processing on the messaging. Another pattern that I want to introduce today, because it is quite helpful, particularly when things go wrong in production, it's the dead letter queue pattern. And here you can imagine that we have a regular producer, it's done sending messages into a queue, and they start getting consumed by consumers until we start running into an exception. So let's say message C starts running into an exception, and it runs into an exception repeatedly. So it runs into an exception, it gets put back into the queue, it gets delivered to a consumer again, runs into an exception, goes back into the queue, and again, and we really don't want that to go on forever. So what we need to do is to ideally take this message offline, because it is either a sign that there is a momentary problem in the system, or it might be that the message can be considered what we call a poison pill. And the poison pill doesn't necessarily mean that there is anything malicious going on within the message. It just means that the message will probably keep on running into an exception, and that's probably because we have made some wrong assumptions in the consumer code, or you know, the payload is simply corrupted and so on. So we take it out by setting up a dead letter queue, and we instruct our main queue that after so many times that the message runs into an exception and comes back, then please take it out and put it into a dead letter queue. And their application operations, or we as developers, can inspect it later safely without, you know, having the hassle that it's in production and that it keeps on running into an exception. Another important pattern that I want to mention is FIFO queues. And it's a requirement that comes up every now and then. And what the requirement says is that we want to maintain a strict ordering of delivering of the messages that comes into the queue. FIFO stands for first in and first out. So if we want to maintain that order for message delivery, what we see is that we have a producer, and it puts the messages into the FIFO queue, and it is the FIFO queue that it guarantees that the messages will leave the queue in the order in which they came in. But as you might imagine, FIFO queues come at a price, because trying to scale messaging systems massively and guaranteeing order is very hard to achieve. So every time you really want to restrict order, you need to reduce at least to an extent. And this has nothing to do with the product that you use or the quality of how it's implemented. It's just simply pure physics. We will need to reduce concurrency, and we won't have that as high a throughput as we would otherwise. But what is also interesting to mention is that we not only have FIFO queues, we also have FIFO topics. And I just want you to be aware that this functionality exists and that it's, for example, available in Amazon SNS. But I still have more patterns to discuss, and I want to mention a few more. And the first one is the messaging filter. And it targets another specific requirement that tells us that maybe we are only interested in a subset of messages from a topic. We know that a topic, we have learned that when we work with topics, every subscriber to the topic receives every message. But what if I'm only interested in 90% of those messages? Here, for example, we have two subscribers, the one at the top and the one at the bottom. And these guys are only interested in getting the green and the red messages respectively. The one in the middle is happy to receive all messages. But for these other two, we need to apply the message filtering pattern. So what the subscriber can do is simply instruct the topic, hey, apply a filter, and only if the color equals green or only if the color equals red, then let that filter pass and send me those messages. So the publisher doesn't need to be concerned about it when we implement this functionality via topics. It's just a subscriber that takes care of instructing the topic as such. And the publisher will remain totally unaware, and that allows us to achieve loose coupling, again, between the publisher and the subscriber, even though we're implementing a little bit more of logic, which is in this case a message filtering. And I bring this to your attention because there are different ways to implement this without message topics, but they will require more effort. The recipient list pattern is one pattern that we can use to achieve or implement the same functionality. And it looks something like this, in which we need to manage a component that takes care of this recipient list, of knowing about it. And it's a standalone component that we can embed between the publisher and the subscribers that knows whoever recipient is and which messages he is interested in receiving, and will implement some code to do that filtering. And this will be some code that we will need to maintain and we will need to operate. It will require some configuration, and it has the potential to introduce coupling between both ends of the communication. So we should ideally avoid trying to implement this ourselves if we can leverage message topics for that functionality. Another pattern for message routing is the so-called scatter-gather pattern. And with this pattern, we try to address the question of how do we distribute requests to a number of relevant parties that might be interested in providing some responses, and how do we capture those responses that they're interested in providing. And a scenario for this is, for example, parallel processing. So we want to distribute processing to a number of parties, for example, to search for the best result that they're able to achieve, or to aggregate responses, and so on. And again, we will have a requester. It can, or as producer or sender, and it will, in this case, it's a requester because it sends a request and we will collect a response. So that's why we changed the names a little bit here. So we have the requester, and it will put, again, a message into the topic. And the message will get pushed to our subscribers, which in this case I call responders. And the responders can work on the request, and they can create the responses. And they can put the responses into a different messaging channel, into a queue, for example. And from that queue, we can collect those responses and, for example, aggregate them and process them into a final single response. As you might remember, I previously introduced the correlation ID and the return pattern address. And of course, we will need to use both of them here because the responders will need to know where to send those responses, what is the address of that queue where the responses are going to be collected. And also the correlation ID, because once we take those responses, we want to know, okay, but to which requests do they correspond? So this request, as we can see here, is again a conversation pattern, because it really is a conversation, a two-way communication between requester and responders. And even though it looks a little bit like a large pattern, again, the nice thing when we work with patterns and when we mention the term scatter-gather is that this will typically come to the mind of people. They will likely be familiar already with this, or they can learn it. And then you don't have to explain this every time. People will know what you mean. And this is a really cool thing about patterns. So as promised in the beginning, I also brought some use cases to make what we have discussed more tangible. And the context for these use cases is called the Wild Rights Company. It's a fictional startup that we have made up within AWS, and it is a company, a fictional company that works in providing individual passenger transformation. Think about Uber or Lyft and these kind of things. And it replaces, our traditional taxi cabs with no less than unicorns, because unicorns are more fun and more magical than taxi cabs. And just to have a little bit more fun, we have a company that provides rides via unicorns. And this company has a microservices based backend, and they run on a lot of or different serverless services on AWS. And let's take a look at their first use case. So the first use case is about submitting the completion of a ride. So the unicorns deliver the passengers to their destination, and then they want to tell the backend, hey, I've completed my ride, so that they can eventually get the money that part of the money that the customer paid for that ride, and which the Wild Rides backend will collect from the customer via some payment system. So the unicorns, the ones that provide the rights, will use their mobile application, and the mobile application will send a post request to their ride management service, which is one of the services that makes up the entire backend, and which resides on AWS. And this post request will contain all the details about the ride, and it will be the service that records that ride completion. And for this, we have chosen to have a managed API gateway component in the form of Amazon API Gateway, because we don't want to deal ourselves with implemented all that logic for API management. So we can just leverage that serverless AWS service. And next, behind it, API Gateway, we have the actual service that processes those requests that come in, those requests to, mark those rights as completed. And that's a piece of code that deals with the incoming request, and it probably stores some of that information that it has received in the database. And then it sends a response to the client. Typically, when we talk about REST APIs, we respond with a 201 HTTP 201 created for a new resource that has been created, and we return a representation of that resource. And so far, it's all very good, but it turns out that the backend is larger than that, and this service that we have here is not the only one that is interested in getting the information about the ride completion. There are other services that would like that information too. For example, we have the customer notification service, we have the accounting service, we have the customer loyalty service, we have the data lake ingestion service, and at last we also have the extraordinary ride service, and this is a special type of service that is interested in receiving information about completed rides that are above a certain fare, so that the customer paid above a certain amount, and that was above a certain distance in kilometers. So how can we integrate those services that we have in the right-hand side now with our service on the left-hand side? Could we use integration via databases? I mean, we already have a database in our original service on the left-hand side, and it's already storing some information. So we could potentially just point all these other services to, to connect to the database and get the information that they need. But we don't really want to do that. This wouldn't really be a loose coupled way of integrating our architecture or to achieve loose coupling in our architecture. This is pretty inflexible, because any changes that might occur in the database by the service that we have had on the left will probably delete or alter the integration that has been achieved with the other services, and things will start to break. So we really don't want to do that. Could we integrate via REST APIs? Possibly. REST APIs are a very good means to also achieve loose coupling. The web architecture is a loose couple architecture, and it's a very large system which is built on REST principles. And yes, we could do that, but of course it comes up with a little bit more effort, right? So we will need to implement the recipient list pattern in this case, and we will need to manage a little bit, a separate component of code that knows about those who those recipients are and knows their HTTP addresses, so that it can send and start distributing the right completion message that came in. So yeah, we ideally don't want to manage that by ourselves. And moreover, we have this special service here that requires us to do some filtering. So we would also need to implement that filtering by ourselves, because he's only interested in some of the messages and some of the rights, and not all. So what if we actually try integrating via messaging? And that is definitely the way to go. So I hope you already guessed that before it was stated here. But yes, it will make things much simpler. So we can add a topic here, an SNS topic, and that topic can publish the right completions to all interested parties. And the services on the right-hand side only have to subscribe to it, and our service here on the left-hand side doesn't need to know anything about which other services are trying to also get that information. And we can further leverage the SNS message filtering functionality to deliver to this special service only those messages that he's interested in and apply that filtering. If we want to add more resilience on the right-hand side here, for example, in the cases that these services are offline due to some maintenance or because they run into a runtime exception, then we can also put some topics here that will keep the messages buffered for a while and safe for a while until our services can return to operation. And once they do, they will simply just continue picking up messages from the queue, and we don't have to worry about losing important information for those services. So I'll try to go a little bit fast on the last slides, and would like to address the scalability scenario here. So customers can also pre-book rights, especially when Wild Rights decides to launch a campaign. We might say, hey, you might write next week, but book now, book this week for a large discount. And we start with an architecture that simply processes all the pre-booking of rights as a whole, at once. And you will see what I mean here. So the request comes in, hey, pre-book my ride, and it lands on the pre-booking service. Again, we have our API gateway, we have our processing resource, our database, and we respond to the client, and yeah, it's all good, right? This is something that we did similar with in the previous scenario. But what if we intensify the campaign and we instead tell everybody to book today? We will have a large load today, and we expect then more traffic. And when the request comes in, we actually would like to deal with that request in a more decoupled manner, even in the context of a single service. So we can achieve that through messaging. And when that request comes in, because it has been submitted by the app to the backend, it can come in via the API gateway again. And what we will do differently now is that we won't process the entire request here. We will only do some small pre-processing to validate that everything is good with the payload, and then we will put things into a queue. And once it's been put into the queue, we can return a response to the customer. We don't have to make the customer wait in the client app. And then the rest of the backend can take its time to do the rest of the processing that we have mentioned at the beginning. So that the rest of the processing can be taken care by introducing a queue that will buffer their resources and allows us to process the full request at our pace and scaling as well. So here we will flatten the peaks that might be coming from the large campaign. And just to make it, for illustration purposes, I've also added another service just to illustrate how the fan-out pattern works. There might be our data lake ingestion service also wanting to receive that that information, and we have it there as well. And yes, I didn't have space for the database because we have our database in our backend, but I left it out this time. And I will actually move now to the last use case to complete my presentation. This is the case of a an RFQ. So um, do you remember the scatter gather pattern? So where we want to gather some responses for the requests that we send. It looked more or less like this. And what we want to do is use this pattern to help Wild Rides implement a use case in which customers don't just take the next unicorn for a ride, but they request the best price from all the unicorns that are in the vicinity. And for that, Wild Rides runs a request for quotes. So we use the scatter gather pattern. Our request comes in again from the app, and the ride booking service in the backend will receive that via post, and it will go to the RFQ processing component. And as usual, we'll store something in the database. And then we can, again, store it in a queue, in a topic, to do the scatter part of the scatter gather pattern, and notify all interested parties. We send a response without having processed the entire thing. We send a response to the client with a link to refresh the status so he knows what's going on, that the request for quotes is still running. And we can configure how long the request for quotes can run. And then the interesting parties, which are the actual unicorns that need to provide their quotes, can be notified. And we will do that via another service that can push notifications to the apps of the unicorns. The topic will publish or scatter those requests for quotes, requests that came in. The unicorns will be notified, will submit their responses back, and we will have a response queue for that. So again, utilizing the response queue address so that the responders know where to send the response, and of course the correlation ID, so we know to which RFQ this is related to. We can then aggregate the responses and simply provide the base quote to our riders. And with that, I'd like to close, but not before providing you some resources. We have a blog series that explains this pattern and these use cases that I just went through, and you can scan this QR code to read more about them. And if you want to try things hands-on, you can also go to this other URL represented in this QR code and try things yourself and do some hands-on learning. And a very special call to action. We really value your feedback. I value your feedback. We really are interested in it at AWS so that we can improve our content, the way we deliver for you. So please go to this URL or scan this QR code and provide us your feedback. And yeah, we'll be happy to also in the future address other topics of interest for you. And yeah, I would like to say thank you very much. Sorry for running over time, and happy to take any questions if there shall be any.
Yeah, we're almost out of time. Diana, thank you. Such a great speech. And thank you for resources, because my question was where the reference architecture and patterns you describe in somewhere in knowledge library in AWS. So let's cover
Absolutely.
just one. Yeah, let's
Mhm.
cover just one. So following your use cases, we have a question related to e-commerce system and, for example, if we would like to build payment gateway. So what kind of
Mhm.
messaging you would recommend to implement such solution in e-commerce?
Oh, that's an interesting one. I believe I mean, there should be established patterns for this. REST is of course a very good way to integrate with payment systems as well. And in typical systems where you have redirection, you also need to specify a return address, probably as a parameter in the URL, but you need to go back to the customer. So asynchronous messaging is, of course, when you don't necessarily need to provide a full response immediately. When you're dealing with payment systems, you probably want to provide that information inline. And that's, yeah, I think you get my point. But yeah, happy to get more information, consult with my retail colleagues and provide you some links on the chat.
Yeah, makes sense. Yeah, probably FIFA principle should be addressed as well, because the right ordering in payments probably uh, makes sense. Yeah. All right. So thank you for your time. Yeah, and support in our conference. and
My
we are
pleasure.
more, yeah, we are moving forward. And
Thank you very much.